Good evening, my fellow scientists. It is Wednesday, December 20th, 2017, and I want to talk about the iron battery. For new viewers, I have been working for the last year on developing an all-iron battery. It has an iron anode and an iron salt cathode. So iron 3 takes up electrons, iron dissolves and gives them away. This has the advantage of being cheap, simple, and fairly safe to play with in your own home if you'd like to attempt such a thing. And I'm working toward finding an undergraduate who can try all kinds of permutations on the different possible separators and cathode materials and current collectors. For today, I have accomplished one small iteration. I have retried the bag cell, retried the Nafion separator, and I have compared the iron chloride to the iron EDTA as a catholyte. So let's get into that. Let's go through the construction. We've got to have a container that's going to be a plastic bag, and we're going to put some iron inside a Nafion pouch, and then we're going to surround that by some carbon connected with a chromel current collector, and we're going to pour some iron 3 EDTA around that. Stepwise, I'll show you how I went through each part. First, I impregnated this chromatography paper with Nafion, and I folded it up into this little pouch. I used about 800 microliters of a solution of Nafion I purchased from Sigma, and let all the alcohol evaporate off of that pouch, and then folded up the iron, that's a steel wool and iron wire, and put that into the plastic bag. Behind that plastic bag is a little bit of chromel wire. The chromel is going to act as a current collector to interface between the catholyte and embedded in a carbon matrix and the interconnect. So there's the carbon. That's a GUITAR, G-U-I-T-A-R, graphitic University of Idaho thermalized asphalt reaction carbon. And I'm going to fill that space with a little bit of iron 3 EDTA. With this syringe, I'm just using a little cardboard holder to hold everything up so that I can load that in effectively. To try to keep air exposure down, I'm going to hold this closed with a couple of binder clips and a couple of pieces of plastic. So there's the full assembly. You can see the chromel wire over here. That's connected to the carbon, which is embedded in the catholyte. And over here, we've got the anode connection, the iron wire. And when I connect that up with a voltmeter, I get 0.6 volts. Let's talk about how the battery performed. So you can see I'm charging and then discharging here over and over again. The charging is where the line goes up, and the discharge is where the line goes down. I'm charging at 0.8 volts and discharging at 0.05 volts. So it's not against a short circuit. It's got a little bit of a resistance to it. And clearly, they are not the same amount of charge going in and out. I'm putting a lot more charge in than I'm getting out. That's less than ideal. Where is that charge going? Probably just to heat, but it's less than even my previous iteration. Here's exactly the same parameters used to charge and discharge an iron chloride cell with almost the same design. Different carbon. I used a carbon felt for this instead of that GUITAR graphitic thermalized asphalt carbon. That may have helped, but I think it's actually an issue with oxidation because the EDTA is just allowing a much faster oxidation in the new cell. So I'm going to try the GUITAR-based connection to the catholyte and an iron chloride cell next, and we'll try to isolate just what is increasing our performance in the older cell. If you like that kind of thing, tune in Monday through Friday. We talked about iron batteries, battery technology, and all kinds of fun science and chemistry right here in the Alleb Lab.